Good morning. My name is Mark Cadies. I'm manager from Lenovo on the software side of Lenovo and ISG. How many people here know that Lenovo does servers? That's always a really good question because most people know we do PCs, we do Motorola phones, but sometimes people don't know we do servers. So today we're talking about servers. So Patrick's from Intel, I'm from Lenovo. We've been doing a set of work looking at VMware AI, private cloud AI, and we've done some testing that Patrick's going to take you through, looking at performance of VMware AI in an environment, using CPUs, using accelerators, those types of things.
Yep.
In a lot of cases, you know, everything that's in the news, you're hearing large language models, you're hearing GPUs, really expensive. In a lot of cases, especially when you're doing inferencing, training, well, not so much training, but other things, you don't require all that GPU. You can get by with CPUs, and we're going to prove that to you today from the testing that we've done. A couple other things, obviously, if you're familiar with Lenovo, Lenovo's in the server business. We have over 60 servers that can do GPUs and CPUs, and we have over 85 solutions in that area. You're going to see a demonstration of the testing and work that we've done. So I'm going to hand this over to Patrick. Patrick's going to take you through it because we only got 25 minutes.
Exactly. So we have just 25 minutes, and I will go very fast with the information. How about that? Yeah, perfect. Okay. It's okay? Once again? Maybe that? Oh. 1, 2, 3? Now. Okay, let's do like that. Okay, so we have material that takes more than just 25 minutes. I have a session about that, even with live demo after this presentation, so you have a time. You can. One, two, three. Yeah, it's loud. Okay. All right. So I will show you some steps which I did to improve AI workloads on CPU through building environment, deployment, AI components, and run example benchmark tests, plus some tuning on infrastructure. So very briefly, we are using meta models. In this example, this is Llama 2 with Hugging Face. Hugging Face CLI is used by Apex to automate benchmarking, to automate deployment. And Intel Python extension toolkit is the repository that helps to deliver AI on CPU, on GPU, and run very easily. Here is even the information about Hugging Face, how we are logging, how we are making double check about logging after using Hugging Face tool command line. All right, 4 steps to prepare environment. First of all, clone Apex repository, which is very simple. This is GitHub. Create environment. We can use Conda. You can use Docker container. I prefer Conda because that helps me to tune everything very easily. Then configure environment. We have a script which does everything for you. And activate environment. You are ready to run examples. Here we have 2 examples how to run AI workload LLM generative to precision, bfloat 16 and int8. We are using deep speed to spread workload to all of the sockets, all of the processes which we are exposing to virtual machine. That helps to saturate multiple sockets, create more sessions, and achieve more throughput. All right, let's jump back to the configuration. So all of the tests were done on Platinum, CPU 8490H, half terabyte of RAM. Storage, it is aligned with vSAN architecture. Then networking RDMA, AI suite Apex 2.2, Llama 7 billion, bfloat 16, input token, output token size, BS equal 1, and kernel 515 to expose AMX instruction to accelerate int8 and bfloat precision. And vSAN default policy out of the box, how we are deploying that, there is no change. All right, let's start talking about what kind of the steps I did to improve AI workload starting out of the box. So we have non-optimized environment, and I'm measuring second token average latency. So response from inference from a model. And our threshold is 100 milliseconds. So we would like to avoid the situation when the second token latency is above that. So we are still here, but the goal of this exercise was much lower with the second token latency. So the goal of the exercise to show that specific configuration hardware can give you better improvement of your results. I did 3 steps: platform tuning, this is step 1, VMware software tuning, and AI workload tuning. So out of the box, normal optimization. Step 1, SNC. So we have a situation when normally we are using non-unified memory access. VMware handles that properly. There is as well a different way of accessing to memory, so unified memory access. Long story short, unified memory access, you have just one memory controller and all cores or processor accessing to the memory through one bus. Latency is static, is repeatable, but bandwidth is lower because you have one bus and you can't extend that, you can't scale it. With non-unified memory access, we have multiple controllers. That's the default configuration, or multiple sockets. So you're accessing to the world in memory through jumping through memory controllers. Latency can be different. It depends when the specific word or memory information is. But bandwidth is rising because it's easier to scale, and you can achieve better results. Here's the diagram of CPU. But I added yet another feature on top of that. I enabled sub-NUMA clustering. What it does, it creates virtual domains. It's dividing CPU into pieces. In this case, I divided one single socket into 2 regions. That gives me possibility to run one AI thread here and the second an AI thread here and multiply results. At the end, that gives me 9% improvement. So this feature can be enabled in BIOS through methods on platform. You can pick between SNC2 and SNC4, and the SNC4 divides into four different regions. So at the end, we have 4 domains. On 2-socket platform, we have in total 8 domains. Okay, so enabling SNC plus P states, so power states, to improve power usability by VMware. That helps to achieve 9% of reduction. Okay. Now let's go to VMware directly. Not sure if someone from you were using that. Who are using latency mode? Yeah, error. I know error, so it's obvious. It is not hidden, but it's in advanced mode, in advanced option of virtual machine. Going there is latency mode. You can pick normal, high, and high with hyper-threading. What it does, enabling high reserves 4 cores to SXI, purely to SXI. And the rest of the cores are assigned to VM or VMs. There is spinning, physical to virtual. And those cores are static. They are not floating. The assignment is static. To enable that, first of all, you need to enable this option here, plus reserve cores in virtual machine and memory. This is mandatory. But be patient. Please focus on that, because my machine has 2 sockets, 120 cores. I'm using 116. The 4 I need to reduce the number of 4 just for SXI. So enabling that and enabling SNC, we have a reduction 13%. So we achieved double digits, which is really cool. Then we are touching tuning of AI workloads, AI model, and we tested greedy algorithm versus beam search. Beam search is default one, and that gives you the most reliable results. I'm saying the generated result from LLM is fruitful. It's very complex, but beam search selects the K most probable token. So it's probing different paths, and at every step gives you the most probable result. Greedy is faster, but less accurate. Greedy choose the most probable token. So it's not going very deeply, it's rather shallow answer, but very fast. It depends from your infrastructure, it depends from your type of workload, it depends from your type of environment or even client, what kind of method you would like to use. If you would like to scale your environment and create multiple sessions without accuracy, big accuracy, you can easily scale that with greedy. If you prefer to have very complex results, beam search. But if greedy is enough for your environment, adding all of the options, so SNC, latency mode, and greedy algorithm, we are able to reduce latency, second token latency, by 46%, which is very, very, very good result. And it is only on CPU. It is not on GPU. We generated that on CPU. In test, as I said on the beginning, we are using input token size 124, so 124 words as a question, and we are requesting 256 at the output. BS8 means we are starting 8 concurrent sessions at once. So more or less, we can compare that to 8 concurrent users. All right, and there's one thing, don't do it. I know that we are migrating quite often VMware environment from one version to the other. We are doing that properly, but sometimes, and I received that feedback as well, someone forgot to do migration of the hardware. So you migrated to the new vSphere, you have new vSAN, everything, but your VMs are still on old virtual hardware. With that mistake, you're not exposing all of the hardware capabilities from platform to virtual machine and at the end to application like AI. And then AI is not accelerated, what you are missing. And we did it with Lenovo. This experiment is published. You have a link here, you can go. But with AMX, this is result with AMX, this is without AMX. With AMX, it depends from the input token size, but we are able to scale up to 16 users per single server. Without AMX, we can put just 4. So density is lower by 4x. So please remember to upgrade even virtual hardware for VMs. Don't forget that, otherwise AMX, all accelerators won't be exposed to virtual machines. All right, my colleague. No, come on, Mark, it's about you.
So I'm going to scare him now.
Yes, I know.
So besides the work that you just saw, there's other testing that we've been doing with Intel, and here's 3 examples. If you'd like, you can scan these codes and see the methodology and the results in these 3 different areas. But you can see we've tried to mix up, some of it is VMware, some of it's on Red Hat OpenShift. Then we go at specific A models using like TorchServe. So we've mixed it up a little bit. Here's 4 examples. So please scan those if you would like. and take a look at them.
All right. So please take the survey. This is my blog. You can read about some research development that I'm doing myself or with a team. I'm blogging as well as the expert. We have a booth in Hall B, so if you have a time, just come and see us. Plus, as I said, I have live demo after this session, so you can come and see what we have, what we are doing in live demo. All right, is there any question maybe? Is there a mic for, do we have a mic? Or, yeah.
I know a lot of the interest lately has been large language models, but
Sorry. Yeah, come on.
I know a lot of
It's not working? No.
Yeah, I know a lot of the interest.
No.
I know. There we go. I know a lot of the interest lately has been in large language models, but has there been equivalent research or benchmarking with small language models? I know that's a much more evolving set of research because of the more quantifiable ontologies involved, and that's a highly interest for specialized environments.
Yeah, that's a very good question. I tested rather small model because 7 billion is not big one, 80 billion like Llama 3, for example. So this is small model. We can improve the results after quantization to different precision, int 8. It's possible, and there was a foil about that. So if you're running on CPU, we are giving you advice to run rather small models, 7 billion on even 13 billion. It's fine. Anything above is rather hard to run without quantization. But that one was an example of small model.
Thank you.
Yeah. Yeah.
A quick question. So I might have missed this in the beginning. We're talking about. Oh, sorry. Ooh, sorry. We're talking about trained models already, right?
This is inference.
Oh, okay. Thank you.
Okay. Anything else? So I have coupons for questions.
Thank you.
If not, then yeah. Yes, of course.
So I know these are CPU-based models.
Exactly.
Are there any modes where you share workloads between CPU, GPU? Have you seen any? Because I see the subnuma breakdowns for the domains. Is there any sort of cross-management between the CPU and GPU yet inside the model, or no?
Inside the model, no. When you are running, you are picking GPU or CPU.
Right.
You are not running on both. Rather, CPUs to control your process of running, and you're running the full inference on GPU. But the IPEX repository allows you to run both, not at once, but if there is GPU, will detect and run on GPU.
So I guess what I'm trying to ask is from a DR perspective, if I needed to, let's say I was running on a GPU model and my GPU crashes or fails, they're expensive, and I need to keep the lights on and switch to a smaller model, is there a failover model for the Gen AI with the CPU?
Well, loudly thinking is the scenario which can be addressed, but rather you should control that. You should have some mechanism to switch between GPU and CPU.
Okay.
Maybe you can have multiple VMs, multiple entries to a model, and just fail over. When one is down, then switch to the other, which is ready and waiting for responses.
Okay, so it would be on the model, like on my side, there's nothing in VMware I could use to configure the failover.
No, it's application level problem.
All right.
Okay. Yeah. All right. If that's all, thank you for your time.